Okay, so I'd like to welcome everybody to a special joint quantum computation and isolation and quantum fluids and isolation. So today I'm very happy to introduce Shiyu Zhou. She got her bachelor's degree magna cum laude from BU 2013 to 2017. She's currently a PhD candidate starting 2017 to present under Professor Claudio Schaman. She is the co-founder of the mentorship program for undergraduates in physics at Boston University from 2019 to present. And she's also the president of the Women in Physics organization at Boston University from 2018 to present. And today she'll be talking about realizing a Z2 spin liquid in D-Wave. So please help me in welcoming, either by clapping your hands virtually or by unmuting and clapping, Shiyu Zhou.
Well, thank you very much for the introduction. Hi, everyone. I'm Shiyu, a fourth-year graduate student working with Claudio Schaman at BU. And today I'm going to talk about our recent work on realizing the Z2 spin liquid in the D-Wave. And this work is done with Dimitri Green, Danny Dao, and Claudio Schaman. So first, I am going to introduce you what are the quantum spin liquids. Specifically, I'm going to review a little bit about the Toric code. And then I'm going to talk a little bit about the physically realizable quantum spin liquids model, which uses only two-body interactions and the combinatorial gauge symmetry to realize the quantum spin liquids. And then I'm going to tell you the actual experimental realization of the spin liquid in D-Wave. Specifically, I'm going to talk about the embedding of the model in the D-Wave and the actual observations of spin liquids in the D-Wave, and also a bunch of variations of the models that gives us also spin ice and ferromagnetics. And at last, I'm going to talk about our current work, which is to actually probe the quantumness of the spin liquids that we are building in D-Wave. Okay, so let's get started. So what are the quantum spin liquids? So the quantum spin liquids dated back to 1973 when Anderson proposed it for understanding the ground state of the antiferromagnetics. And at 1987, Anderson, Bhaskaran, and Zhou tried to use it to understand the phenomenon of high temperature superconductor. And not until 1997, Kitaev realized that one can use quantum spin liquids to do topological quantum computation. So those are the histories of quantum spin liquids. So what are actually the definition of quantum spin liquids? So what are they? So for the quantum spin liquids, it lacks any kind of magnetic ordering in the ground states. And the ground state also has high degrees of entanglement, hence has massive quantum superpositions in the ground state. And there are bunches of exactly solvable models of quantum spin liquids. The first one is this famous Toric code realized by Kitaev in 1997. And then there's this fractal model realized by Claudio Schaman in 2005. And there's also this Kitaev honeycomb model realized by Kitaev again in 2006. So now I'm going to give you a little bit review of the Toric code, which also known as the Z2 quantum spin liquid. So the Toric code lives on the square lattice, periodic, has the periodic boundary condition on both x-axis and y-axis. And the Hamiltonian of the Toric code is the sum of the star operators A and the plaquette operators B. So the star operator is just the product of all of the sigma z on the spins of a star. And the plaquette operator is just the product of all of the sigma x on the spins along a plaquette. And this Hamiltonian has a couple of nice properties. Well, first is that all of the star operators commute with each other because they either don't overlap or they completely overlap, but they're the same kind of Pauli operators, so they commute with each other. Similarly, the plaquette operator commute with each other as well. And also, each plaquette operator and star operator commute with each other as well. So they either do not overlap at all, they commute, and if they overlap, they always have two spins overlapping, and if you carry out the calculation, you will find out they commute. And because of that, the star operator actually commutes with the Hamiltonian, and similarly, the plaquette operator commutes with the Hamiltonian as well. So because of those nice properties, we can define the ground state of Toric code to be the plaquette operator and star operator being equal to 1. And this gives us the ground state. Basically, the ground state consists of bunch of the superposition of all of the possible loop configurations on the Toric code, which the red loop here donates the ground state in the Z basis, and the blue, it's blue, blue loop donates the configuration, ground state configuration in the X basis. And we also see there are open strings in the Toric code, and that actually will give us excitations. So Toric code was already realized in 1997, but it's very hard to actually realize it physically in the lab because of its 4-term interaction nature embedded in the Hamiltonian. But can we really not, is it really not possible to realize Toric code in the nature? And if it's possible, how can we realize it? So on the 2019, 2 years ago, Claudio Shimon, Dimitri Green, and Zhichen Yang, they came up with special Hamiltonian that utilized only 2-body interactions to construct the quantum spin liquids. And they also invented this combinatorial gauge symmetry so that they can use 2-body interactions to construct the quantum spin liquids. So here's that model. Here's how the model works. So we have this usual star, but in the Toric code, we only have spins on the link. But in this special Hamiltonian, we are going to put 4 gauge spins sigma on the link and 4 matter spin mu on the vertex. So for each single star, we will have 4 gauge spins sigma and 4 matter spins mu. And the Hamiltonian of the single star follows this one. We can see that each sigma, which is the gauge spin, only couples to the matter spins, but do not couple to the rest of the gauge spins. And similarly, each matter spin only couples to the gauge spins, but do not couple to the rest of matter spins. And the interaction between the gauge spin and matter spin follows this doublet matrix. And this doublet matrix is basically the combinatorial gauge symmetry. It is basically the spin permutation plus spin pi rotations. We can see that the element of the doublet matrix is basically +1 and -1. -1 represents to the pi rotation, +1 represents the spin permutations. And according to this doublet matrix, we can see that each gauge spin only couples to the adjacent matter spin with an anti-ferromagnetic bond, which is this minus here, and couples the rest of the 3 matter spins with a ferromagnetic corresponds to this +1 over here. So this is how the single star works in the special Hamiltonian. And now we can zoom out, connecting all of the stars together. I have noticed that 2 adjacent stars will share a gauge spin. And the Hamiltonian will just be the sum of all of the star operators. And the quantum fluctuation of this model comes from the transverse field on all of the matter spins and the gauge spins. So in the limit, when the gamma is much larger than J, we can effectively integrate out the matter spins in each vertex and left with this effective Hamiltonian, which you can see the first term is just the star operator in a normal Toric code, and the second term is the transverse field on the gauge spins. And if we treat this gamma 2 perturbatively, we can see that the lowest surviving order in the perturbation theory is exactly a term that flips the spins along the plaquette, which gives us the Toric code limit. And this is also being confirmed by the quantum Monte Carlo done by Kai-Xin Wu from the Anders Sandvik group in BU. And we can see that this red line is separating the Z2 quantum spin liquid phase and confined phase, and it is derived from the theoretical predictions. And then the dotted line here is the actual quantum Monte Carlo results. We can see that this model indeed gives us the Z2 quantum spin liquid phase. Okay, so now we have the special Hamiltonian that can use only two-body interactions and the combinatorial gauge symmetry to realize the quantum spin liquids. The question is that how can we actually build it? Right. So technically, we are still a group of theorists, so we are not going to actually buy some cryostats, superconductors to actually do the experiments. Instead, what we are going to do is we are going to realize the model in the D-Wave. So D-Wave is known to be the quantum annealer. It starts in the basis of X spaces and slowly anneal to the Ising type of Hamiltonian that you can embed into the D-Wave. And the D-Wave is made of superconductors and Josephson conjunctions. It has in total 2048 qubits. And now they have a more advanced version called Pegasus. In the Pegasus, they have more than 5,000 qubits, but for this experiments we did, we only used the older version. And this older version, 2000Q D-Wave, each qubit follows this chimera graph architecture. Basically, it tells us which qubit can couple to which qubit. We can zoom in to see the details of the chimera graph. So each star thing in the middle is the unit cell, and inside of each unit cell, we can see we have 4 horizontal qubits and 4 vertical qubits. So each horizontal qubit is only coupled to the vertical qubits, but not to the rest of the horizontal qubits. And similarly, each vertical qubit is only coupled to the horizontal qubits, but not to the rest of the vertical qubits. So that is the inner unit cell coupling. So what is the couplings between the unit cells? We can see that for each vertical qubit, it only couples to the qubits from corresponding qubits from adjacent left and right unit cells. And each horizontal qubit is only coupled to the corresponding qubits from adjacent above and below unit cells. So that's basically the chimera graph. And we can see that the connection, the qubit and qubit connection, is rather constrained. So the problem here is that how can we actually embed our Hamiltonian into this chimera graph? So this is the embedding we came up. It's called tilted embedding, and it's designed by Danny Dao, who used to work at D-Wave. And it looks quite complicated, but I'm going to walk you through this. And let's first focus on this 2x2 square box here. So in this box, we have in total 4 stars. Only 2 of them, we are actually going to embed our stars into it. And one of it right here, we are not going to use them. And right here, we are actually going to put the ghost spins into this unit cell. And the ghost spins functionality will be clear later, and it will be clear why we call them ghost spins. And recall our star Hamiltonian has 4 gauge spins sigma and 4 matter spins mu. And each gauge spin only couples to mu spins, but do not couple to each other. So that's exactly what chimera unit cell is doing. Each horizontal qubit do not couple to the vertical qubits. So if we put our gauge spins on the vertical qubits in the unit cell and matter spins on the horizontal qubits in the unit cell, the chimera connection kind of takes care of the star embedding. The only thing we have to make sure is that for the gauge spins, it couples to one of the matter spins with an anti-ferromagnetic bond, and the rest 3 with a ferromagnetic bond. Only one of the gauge spin coupling is shown, but the rest should be the same. So now we know how to embed a single star in the D-wave, but the question is, how can we connect stars together? Remember, two adjacent stars are supposed to share one gauge spin, but it's very hard to make the two independent unit cells to share one gauge spin. So how can we do it? So here we're going to use the ghost spin. We're going to copy the value of this gauge spin to this ghost spin with a strong ferromagnetic bond. And then we're going to copy the value of this ghost spin to this one. And then we're going to copy the value of this ghost spin to this gauge spin from this unit cell with a strong ferromagnetic bond. So what we are trying to do is that we are trying to use those ghost spins to copy the value of this gauge spin to this gauge spin, so that we make sure that those two gauge spins always share the same value. So effectively, we are using the 4 spins to create one gauge space. Okay, so that's how we actually gonna couple connect the adjacent stars together. And now we can zoom out. We can connect this stars with this star in the same manner, and this star with this star, this star with this star. And with 4 stars being connected, we have a plaquette. And notice that the plaquette is a 45-degree tilted, and that's why we named this embedding tilted embedding. And then we can, rotate 45 degrees back. We have this our more familiar version of the square lattice. We have 4 matter spins in each vertex, and 4 qubits, 4 spins to represent one effective gauge spin on the link. And this is just configure for you to compare with our embeddings. And although we are using 4 spins to represent one gauge spins, the symmetry, the combinatorial gauge symmetry is still respected, because essentially what we are doing is just copying the value of gauge spins. So now I have the embedding of our model into the D-Wave. Now I can actually do the experiments. So here I am at my home in Boston with my dog and cat in the pandemic. And here is the D-Wave machine in the Los Alamos. And I sit at home, program the embedding, and send it to D-Wave along with the instructions of how I want the annealing schedule be, and how many samples I want to have, and some error correction instructions. And I send them to the D-Wave using through the API, and the D-Wave process all of the informations and conduct the experiments, and at the end measures the qubits in the Z basis and send me back the plus or minus values of each qubit. So remember that our Hamiltonian, we have transfer field on matter spin and gauge spin. And also because we use the 4 spins to represent one effective gauge spins, the transfer field on the gauge spin should be the order gamma to the 4th, where gamma is the transfer field on the matter space. So that's why we suspect this is what happens inside of the D-Wave experiment. So we start at the beginning of our annealing path, which is when the state is in the ground state of the sigma X basis, and the gamma and gamma tilde is in their maximal value. And then we slowly turn down the gamma. We going through this paramagnetic phase and cross this boundary going into the quantum spin liquid region. And then we end at this classical endpoint when gamma and gamma tilde are both 0. And then we do the measurements. Okay, so this is what I suspect to happen. And now I have all of the data. The question is, how can I know that I actually have a spin liquid? So one of the best way, or if not, it's the best way to say that we have a spin liquid is through the visualization. So here I present a typical configuration of the samples taken from the D-Wave experiments. So each link here represents one spin. Actually, it represents one gauge spins, and the matter spins are not shown here. And the gold color represents spin up, and black color represents spin down. And the white area in the middle of the sample indicates the broken qubits of the D-Wave in Los Alamos. And if we look at this configuration, we can see that the configuration is really made of a bunch of connected strings. They are not connected loops. It's because we are not using periodic boundary conditions. Rather, we have this open boundary conditions, and we have actually a lot of boundaries. This internal host gives us boundary as well. But all of the strings, connected strings here, they either terminate at the internal boundary or they terminate at the external boundary. For example, this one that I labeled in red. It started with the internal boundary and traversed a long way and ended at the external boundary. So this is just a typical configuration we get from thousands of samples from D-Wave, and the majority of them will have this, give us this connected string configurations. So we are fairly confident to say that we successfully built the Z2 spin liquids, but we actually can do more with these models. Remember that the gauge spins and matter spin interact through this W matrix. And if we deform the diagonal of this W matrix with the amount eta, and when eta, we found out that when eta is negative, that means the diagonal of the W matrix is going to be more and more negative, we will have spin ice. And when eta is exactly 0, we will have the Z2 spin liquid. And when eta is positive, the extreme case will be when eta is equal to 2, the diagonal will just be 1, which will just give us the ferromagnetic phase. And here are the configurations of different phases. The panel A shows the Z2 spin liquid when eta is 0, which I've shown in the previous slides. And the panel B is when eta is negative 0.2, which we have spin ice configurations here. We see that for each connected loop, none of them are self-intersecting, which exactly follows the ice rule 2 in, 2 out. There's no for all spin up. There's no all spin up or all spin down stars. And in panel C and D, I show the configurations of the ferromagnetic phase when eta is equal to 0.2, and panel C shows all spin down cases, and panel D shows a configuration with domain wall separating the all spin up and all spin down domains. So now with this model, we can create essentially 3 different kind of phases, but we can also try to figure out the phase diagram among those 3 different phases. So Z2 spin liquid is also known as the 8-vertex model, where each vertex has to satisfy the parity being 1 constraints. And we group this 6 vertex to be the 6 vertex type because they're essentially the 2D spin ice. And then we group this 2 vertex type to be the 2 vertex. They are either all spin up or all spin down, which is basically the ferromagnetic cases. And then it is known that when A and B equals to 1, those A, B, C, D letters represents the weight of each vertex. And when A and B equals to 1, this 8-vertex model is known to have this phase diagram. The solid black line indicates the 6th vertex, and in the middle we have this 8-vertex region, and outside we have this non-8-vertex region. And when D is equals to, or when C is also equals to 1, we can see that when D is equal to 0, we have the 6th vertex, and when we increase D, we goes into the 8-vertex region. But when we increase more and more, when D is larger than 3, we will exit the 8-vertex phase and enter into the ferromagnetic phase. And D is nothing but the Boltzmann weight of the 2 vertex over the 6 vertex, which in our case is just e to the 4 eta divided by t, and t is the temperature. So that gives us this following phase diagram. So the x-axis is the eta, and eta is the deformation of the diagonal of the W matrix. And the y-axis is the temperature. And the orange line here is separating the 8 vertex region and the 2 vertex region. And when temperature is 0, the negative eta gives us the 6 vertex region, which is the spin ice. And because the D-wave operates at non-zero temperature, it operates at 15 million Kelvin temperature. So the experimentally allowed region is technically this dashed box right here. And then I'm going to show you some actual data we take from the D-wave experiments. So here I'm plotting the density of the 2 vertex type. Remember, the 2 vertex type is the spin up and the spin down. Oops, somebody's entering the room. Okay, and the x-axis is the eta, and the y-axis is the temperature. And it's going to be the effective temperature, not the actual temperature. And we can see that when eta is positive, the density of the 2 vertex type is approaching the value of being 1, which means we have the 2 vertex type. And when eta is negative, the row 2 is approaching the value of being 0, and that means we are entering to the 6 vertex type phase region. And then exactly in the middle, we have we have row 2 being a quarter, and that gives us the 8 vertex type. And we can also calculate the probability of each vertex across different eta at base temperature. And we can see that when eta is negative, the 2 vertex type is heavily being suppressed, and the 6 vertex type are equal probable. And exactly at eta equal to 0, all 8 vertex type are equally probable, which again confirms that we have Z2 spin liquid. And then when eta is positive, the 6 vertex is heavily suppressed, left us with this 2 vertex type. So we also calculate the average magnetization squared, and we can see that only in the ferromagnetic phase we have non-zero magnetizations, and in the 8 vertex and 6 vertex region we have no magnetic orders, which again confirms that we have the spin liquid. And finally, we collapse the row 2 and square those 2 parameters against the parameter eta over tau, and we see that they all collapse on top of each other nicely. So again, shows that those 2 parameters are being controlled by the eta over tau parameters. So at this point, we are fairly confident saying that we built the classical Z2 spin liquids and the spin ice and the ferromagnetics, but we can't say that we actually built the quantum Z2 spin liquids. Can we do anything? Can we probe anything quantum in this setup? And the answer is yes. So this leads to the current project that we are doing. It is inspired by the paper Coherent Propagation of quasi-particles in topological spin liquids at finite temperature, which is kind of what happens inside of D-Wave, because D-Wave operates at a finite temperature. And this paper is done by the group in Cambridge, and we are collaborating now. So the question is, can we probe anything quantum? Can we observe signatures of quantum spin liquids? So remember, this is what we suspect happens inside of the D-Wave experiments. We first start in the paramagnetic phase and cross the phase boundary into the Z2 quantum spin liquid region, and we end at this classical endpoint, and we do the measurements. So the question is, can we probe anything in this red region? And the answer is yes. We can use this reverse annealing technique in D-Wave to probe the red region. So what does reverse annealing do? It basically, instead of starting the initial states here, instead of starting the experiments at this point, we are actually going to start those experiments at this point. So at this point, it was before, for the forward annealing, we are, the initial state is in the ground state of sigma x spaces, and the transverse field are in its maximal value. But in the reverse annealing setup, the initial transverse field are going to be 0, and the initial states are going to be the initial state that I feed into the system, which in this case will be our Z2 spin liquid phase, plus an excitation created on one of the stars here. And so what we're gonna do is that we're gonna quickly ramp up the transverse field, which in this diagram corresponds to that we goes back along the annealing path to a point where the gamma is not 0. And we're gonna let it to sit there for some amount of time, and then quickly turn down the gamma, which in this diagram just means we go back to where we start. So why can we do this? Why do we do this? It's because if we turn up gamma for too much, for too high values, we are actually going back to the paramagnetic region. However, if we turn up gamma for the correct amount, we are actually going back to the Z2 quantum spin liquid region. And we can see that how does this created excitations in this Z2 spin liquid going to propagate inside of the Z2 spin liquid. And this excitation, technically, we can call it spinon. And then what we can do is we can measure the final location of this spinon, and to see if this spinon propagates quantum diffusively or classical diffusively, to probe the quantumness of this D-wave, or to probe the quantumness of our setup in the D-wave. And so what exactly happens is that we have this Hamiltonian. The first term is the star operator, and then we have this transverse field on the spins, on the gauge spins, and the plaquette operator is on the order of gamma tilde to the fourth, and for the spinon hopping is on the order of gamma. So if we turn up the transverse field, what's going to happen is that the spinon is going to hop around inside of the sample, given that there is some flux going through some plaquettes. And hopefully we can see that the spinon is going to propagate quantum diffusively. And here I am showing some preliminary data of the spinon propagation. I initialized the spinon in the center and turn up the gamma for some amount of time and see the probability where the spinon end up to be. And hopefully we can observe something in this setup. And with all that said, thank you for everyone's attention.
Okay, so if anybody has any questions, so I actually have some questions, but first, I'll leave it to the audience. If they have any questions, they can ask first. So please feel free to unmute or raise your hand. Okay, maybe I'll ask some of my questions. So, I mean, one thing I was thinking of as like a potential long-term application of this, could you use, let me try to word this correctly. Could you try and use the D-Wave device to, in a way, simulate, say, a system with Fibonacci anyons, and then like going beyond the Toric code, right? And then try and simulate like a topological quantum computing on this regular non-topological quantum computer. Do you see what I'm saying?
Yeah, I think this is what we are trying to go toward. Okay. I think initially this group came up, this Hamiltonian is what they have in mind is hopefully they can create the they can create a Toric code in the D-Wave. And this is just the first step that we are trying is to actually realize the classical spin liquids, which is the classical toric code in the D-Wave.
Yeah.
And now what we are trying to do is that since we realize the classical, can we say anything about if we can realize quantum spin liquids or not? And also in our paper we actually commented on that if D-Wave can allow us to have the access of the y direction interactions, and then we can actually create toric code, because in their paper they actually have a model suggesting how actually we can do it in D-Wave to create the toric code. But really the reality is that D-Wave does not have the control of y direction connections. So that's why we are very hand-wavingly trying to create spin-ons in the sample and to see how does it propagate, to see if it's quantum or not. But in order to actually fully embed the toric code, we need the y direction control as well.
But these would be abelian anyons, right?
Yeah. Toric code will be a billion anyons. Yes.
Yeah, so how would you go like a step beyond toric code, right? So how would you actually simulate non-abelian anyons?
So for this setup, I believe it is for this 2D setup, I believe it's not possible to have the non-abelian anyon. But I think in their paper they might have the similar setup, but for the 3D fractal basis. And I think in that case, you might be able to create non-abelian anyons. But again, I don't know actually how that could be realized in the D-Wave yet.
Okay. So anybody else? Does anybody else have any questions? Please feel free.
I see a question in the chat.
Oh, there was. I can't see it. It must be just to you.
Oh yeah, I can see that. So the question is that. Well, thank you for saying that. And also the question is, D-Wave seems to be very good for this sort of experiments / simulations. Oh, I guess it's not a question. Well, I guess maybe like what kind of experiment / simulations? Yeah, they're good at. I think they're better for what is it, for optimization problems. And what we are trying to do here is trying to fabricate phase of matters into the D-Wave. And luckily we can do it because we have this Hamiltonian that has two body interactions and this combinatorial gauge symmetries. And also luckily we have this embedding to actually realize our Hamiltonian, but it really has to be case by case saying that, what can you do in D-Wave? Originally, I think it's meant more for optimizations.
Okay.